Hey-o! All right, guys, good morning. All right, so today's lesson is chapter 30.1, Faraday's Law and Lenz's Law. Um, in order to understand fully Faraday's Law, the first thing we need to do is figure out this concept called magnetic flux. Now, we've already covered this with electric fields. If you'll recall, electric flux was the measure of an electric field piercing a surface. Okay, it was the area integral E dot dA, right? Well, magnetic flux is very similar. The only difference is that it's the measure of a magnetic field piercing a surface. So we're going to write our expression for magnetic flux the same way. It's the area integral of B dot dA. So instead of an electric field, we have a magnetic field. If you'll recall, this is a scalar product. The magnitude of the magnetic flux is just going to be the magnitude of the magnetic field. The integral dA is not even really a real integral. It's just the area of whatever we're talking about, right? The integral of dA is A. And the dot product gives us that cosine of the angle in between those two vectors. Okay, if you'll recall, say we have some surface. We've got a sheet here, and we're going to establish an area vector that is normal to the surface, right? Normal to the surface there. And then whatever magnetic field is piercing through that surface, let's say it's going this way, right? The surface, there's our magnetic field, right, at all points there. Then the angle in between that magnetic field and the area vector is our angle phi. Okay? Right, the units of flux are what are called Webers. All right? 1 Weber, the WB, is equal to a Tesla times the unit of area, which is meters squared. Okay, there's our SI unit of magnetic flux. It's a Weber, and 1 Weber is equal to 1 Tesla meter squared. So that's the magnetic flux. We've already covered it with electric flux, so I'm not going to spend too much time on it, all right? But we have to understand that it's a thing in order to understand Faraday's law. So what Faraday's law does is it says if there is a changing magnetic flux in the presence of a conducting loop, then what will happen is a EMF will be induced in that loop. Obviously, an EMF will drive current, and that current itself will have its own magnetic field associated with it. All of those things are what we call either an induced EMF, an induced current, or an induced magnetic field. This is Faraday's law of induction. All right, so here's what it states, that Faraday's law states that an EMF is produced when there is a changing magnetic flux. So we get the rate of change of flux gives us some EMF. Now this is true for 1 loop, it's true for 10 loops, it's true for 22 loops, 22. All right, it's true for any n number of loops. All right, and actually we figured this out. There's a video that Dr. Sidden did, which I linked in our Google Drive. If you have, say, a loop here, right, and it's connected to an amp meter, then this thing can move. It's got all our amperage there, right? We've got some conducting loop. Now, what we do with this is we make a changing flux through that loop with a magnet. Okay. Here we've got a north side, a south side. If you recall from magnets, the magnetic field points away from north, points towards south, right? And these loop around. This is a magnetic dipole. That wasn't a very good magnetic field line. But what you can imagine is we move this magnet closer to the loop, more and more of those magnetic field lines penetrate the area of the loop. And when those lines are penetrating, right, as that's changing, then we get a current. And if we pulled it away, then less and less of those magnetic field lines would be penetrating the area of the loop, and again, we'd get another current in the opposite direction. All right, so that is Faraday's law. Now, Lenz's law, or what we like to call as Lenz's portion of Faraday's law, tells us the direction of the EMF. So Lenz found out that when this situation exists, when there's a changing flux, the EMF is induced in such a way that the current associated with that EMF and the induced magnetic field associated with that current are going to be in such a direction that they oppose the change in flux. So if you have an increasing flux, then the induced magnetic field will be oriented in the opposite direction to oppose that increase. If you have a decreasing flux, the induced magnetic field will be in the same direction in order to keep it large, in order to oppose that change. This is signified by adding in a negative sign right here. And then that's the complete representation of Faraday's and Lenz's law. Now remember, that negative sign just has to do with the direction. We get all the magnitude of the voltage there right from this EMF based on the rate of change of that flux. Okay, let's do a quick example. Just to reinforce Lenz's law. Let's say I have a loop like this. It's in the plane, the horizontal plane. Say there is a magnetic field, in the downward direction that comes and it pierces through our loop. And let's say that the strength of that magnetic field is increasing. All right, it's getting stronger in the downward direction. Okay, so in order to figure out the direction of the current, we know that Lenz's law states that it's going to oppose the change in flux. So I have a downward facing magnetic field that's increasing. It's getting larger that way. So therefore, the induced magnetic field would oppose that change. It would be oriented in the upward direction. There's our induced field. Oops. There's our induced field. Now, how do we determine the current based on that induced field? Well, remember, that comes from the right-hand rule, right? So we're going to take our thumb points in the direction of the induced magnetic field, our fingers curl around in the direction of current, and we would see that the induced current goes around in that direction. Okay, that's it for the lesson. Next we'll do a sample problem. I hope you have a great day.